Okay, we continue our slides. So what we've done so far is also called post-training quantization, because we do the quantization after training. And as listed in the previous slides, this is a common method. I mean, you can do it, and I recommend you to do it, because most of the time you won't have the chance to do something else, because some people have trained AlexNet, you don't have their system, you don't have their data set. I mean, you have the data set for AlexNet, but imagine you have an example you don't have the data set for, and you have to put it in an embedded system. In that case, post-training quantization is a nice method, but the actual way to do this is something called quantization-aware training. So you apply quantization during training. And as I've said many times today in these video sessions, we are going to discuss it in this week's slides. It is not better. I mean, post-training quantization is not better than quantization-aware training. Why? Well, people have worked on this. Recent publications have shown that there are cases where post-training quantization to especially integer 8 doesn't preserve the desired accuracy. And actually, we have done a similar example. Well, to int 8, only quantizing the weights even have lowered the probability of the tabby, that cat picture. So you're losing something. And there are very nice papers if you want to just observe them. Benoit, 2008, very nice CVPR paper, Quantization and Training of Neural Networks for Efficient Integer Arithmetic, Only Inference. So you can see these. There's a very nice discussion here. This is a very nice paper. And also Krishnamurti, 2008. It's also a very nice paper on this subject. I have problems with the internet. Okay, while it comes, let's continue. So before we get to quantization-aware training, let's discuss a few titles which cannot be classified for quantization-aware training, but is also different than post-training quantization. So we can do more aggressive post-training quantization. By aggressive, we mean using less precision, not integer 8, integer 4, integer 2, integer 3, integer 1. It's binary. So, but we have experienced that, and we have discussed this in the slides, naively quantizing an FP32 model, a single model, into, for example, integer 4 directly, just like we've done for integer 8. Well, that usually incurs significant accuracy degradation. And we've done this in the video session example. You remember we have changed the bit precision to 4, and it was something else. It was not even a cat. I mean, at precision 6, it was an Egyptian cat, but at precision 4, it was not even a cat. So you lose things. So how to improve? Actually, there are a couple of methods we can list. For aggressive post-training quantization, we have some strategies. Let's cover those strategies. The first one is replacing the activation function. Well, the fastest and most common activation function is ReLU, which is unbounded, which means if the value that enters a ReLU layer is positive, there's no limit to it. If it is positive infinity, you just pass positive infinity. Dynamic range is not limited for the positive inputs. This is very problematic, guys, because if you're using, for example, integer 4, and or below, precision below, integer 2, integer 1, due to very limited range, well, that unlimited range, dynamic range is a problem for us. So what you can do is, for example, Zhu et al. In 2016, or Mishra et al., they use a clipping function for hard-coded values. They clip the dynamic range. So instead of using ReLU, they use a layer called the clipped ReLU. Clipped ReLU is also used in many applications actually today, but they've applied clip ReLU for the use of aggressive post-training quantization. You can just get a paper. So the previous paper you can see quantization deep convolution networks for efficient difference, and this is the DoReFa net. So for low bit width, they used clipped ReLU and they find some accuracies. Just take a look. Or you can use a clipping value which can be different per layer because the dynamic range for each layer changes. We've experienced this. So why use the same clipping value? So if you use different clipping values, you'll have better accuracy. And this Choi et al. In 2018 is a parameterized clipping activation for quantized networks. This is a nice paper as well. I strongly recommend reading it. So that's one of the ideas. Or another idea is you could modify the network structure. So quantization is, in the end, is a loss of information. But if you use some strategies like using wider layers, more channels, maybe you could just compensate for that loss of information. Actually, Mishra et al. In 2018, they tried to compensate for the loss of the information due to quantization by using wider layers. They use binary quantization of parallel binary quantizations, and they sum it up. So they create this inception-like module, which is binary. However, it has more models. So you're modifying the network structure, you are making it a bit more rich. However, you are lowering the quantization value. So you can use a processor which can process 2 bits, 4 bits, but you're using a more complex architecture. That's an idea. Well, some other study, Lin et al. In 2017, they proposed a method they aim at approximating full precision weights with linear combination of multiple binary weight bases. Just like the previous one, they propose a module in which they use parallel binary convolution, and they try to approximate the full precision. So that's how you do it. You modify the network architecture, you make it a bit more complex, and you get better results. That's another strategy to do it. Okay, let's continue.